super random, it was super weird, it was right here at the end of the chapter of triangles and all that jazz, but the reason is because even though they're complex numbers, the math, Pythagorean theorem, the math, r cosine theta, r sine theta, like magnitude cosine theta, magnitude sine theta, the math is a lot like vectors. That's why we're doing this. But these formulas here at the end, they're not like vectors, sadly. They're not like vectors. But you're going to be given formulas if you go into any sort of STEM fields at all. You're going to be given formulas and need to know how to use them. So I'm just seeing if you can take a formula and say, okay, I can apply what I know. So in the multiplication, how did well, I didn't even finish it. Let's go ahead and finish it. 2 times 6 is 12. And how did I get 12? The rule says, yeah, multiply the r's. Multiply the r's. And then how did I get the pi over 4 plus pi over 12? Well, the formula said, add the betas, right? Now, to get those together, we should hopefully all recognize they have different denominators. So let's make them, common by multiplying by 3 over 3. Does that work? We can do that on both, but ultimately when we do it once, we'll do it twice because what's in one is in the other. So what's 3 pi over 12 plus 1 pi over 12? All right, now think about it. 4 over 12, does that reduce? AJ says yes, and I agree with her. Pi over 3 plus I sine of pi over 3. Dun, 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 dun. Don't have to finish it unless they say write it in standard form, but they don't. They say leave it in trig form, so I get to leave it with the theta right there and the 12 out there and just say I'm done. But for those of you guys that did homework, standard form, you would multiply the 12 and you would actually solve with a calculator, with unit circle. Standard form would just say, hey, keep going. Trig form says, nope, done. For those of you trying to use the division property, what's something that you tried to do in order to plug in this z1 divided by z2? What'd you do? Yeah, no.
I just started to plug in.
Yeah, good. And when you plugged in, what'd you get?
Cosine, or parentheses 4.3 minus 2.1.
Good. I'm going to write it down just because it's going to get a little bit long. But yeah. It looks a little bit funny, but Noah looked at the formula and said, hey, I see I'm supposed to subtract thetas. The thetas are the things that come after cosine, so you just took 4.3 and 2.1 and plugged it in. And then, Noah, to finish it off, then you had to write
I sine.
Good.
And parentheses 4.3 minus 2.1.
Good. And someone help him out. What's he missing at the very, very beginning? 5 over 4. So take the r and the r. Just take the two numbers and divide them, say 5/4, whatever. And then for simplifying all of this without having to do all kinds of crazy trig identity simplification, the formula makes it so much faster and easier. And then hopefully, kiddos, we can look at this and say, psh, I can subtract that. Some of you mental mathers, you already have the answer. Some of you non-mental mathers, just think 2-column subtraction. 4 minus 2 is, and 3 minus 1 is. So I can just say this is 5/4. Cosine of 2.2. I guess we don't even need the parentheses. It's kind of obvious. The 2.2 goes in the cosine. Plus I sine of 2.2. And the reason I had to put big old parentheses is because the 5/4 is times the whole thing. We have those formulas, and you don't have to memorize them. Do you know how to use them?
Yes.
Does it make sense? Plug in the r's, plug in the thetas, and if you can add, do it. And if you can subtract, do it, and then you're done. Okay, so there's only really one more thing. We learned on Friday how to multiply and how to divide complex numbers in trig form. We learned what trig form was with the angle and with the r's, with the cosine plus I sine theta notation. We learned how to go from trig form to standard, how to go from standard to trig form using formulas. And now we only have one more thing to talk about, and that's powers. Only one more thing to talk about. Those are powers. And this thing called de Moivre's theorem. Once again, the guy who wrote a math book that basically had this stuff in it. Now, I'm just giving you a peek as to how we would have tried to do this if we didn't have this formula. If we didn't have this formula, we would have to take, now, thank goodness we have a formula. But if we didn't, we'd have to multiply in order to square a complex number. We'd have to take it, and like I've taught you all year, in order to not kill a puppy, to square a binomial, multiply it by itself. I'm not going to go through all the math, because long story short, we do have a formula. But long story short also, some of you can follow this. I'm just going to give you a peek. If we were to multiply, the r would end up being multiplied by the r. Remember, 2 times 3 is 3 times 2. I can rearrange multiplications. So I could switch the place of this big old nasty thing with the r. Bless you, and I would get r squared. But then, because I could move that r back here, I could move its place. And if I moved its place, then I could go ahead and FOIL that second piece. So I could literally do the first, the outer, the inner, the last, and I could multiply it all out. And I would end up with cosine squared theta plus 2I sine cosine theta plus sine squared theta. Ooh, that does not look as squared, I apologize. Here's the dealio. The sine squared theta would also have an I squared to it. I guess I could actually write it the other way. That might make a little more sense if you were actually trying to follow the math. It would be I squared sine theta. Some of us might recognize this little I squared guy and say, hey, complex number. Doesn't he change to be -1? Don't do it. Because then what I can do is say cosine squared minus sine squared. Oops, I didn't write the squared. Again, struggle. Cosine squared minus sine squared. Some of you might remember that's a double angle property, and that's the double angle property of cosine to theta. If you take cosine squared minus sine squared, that's cosine to theta from the double angle property from the last chapter. And some of you might see this little guy. If I look at the 2 sine cosine, 2 sine theta cosine theta, that was a double angle also. Anybody remember which double angle? It's sine. And not squared though. Yeah. Sine 2 theta. And that was only with the square. Look how much work that was. We had to rewrite it, then we had to FOIL it, then we had to go back and access 2 different trig properties from the last chapter in order to be able to get here. This formula says, give me any power, and you're always going to end up with r raised to the power of what you're trying to do. R raised to the same power of what you're trying to do, and the cosine and the sine having this power in as a multiple angle. De Moivre's theorem says if you're raising z to a power, the r is going to be raised to that power, and the cosine and the sine are going to suddenly have that power. Not suddenly, it would actually take a lot of work to get there. But would end up with a multiple angle of that power. So when we come down here, all of us can agree, hopefully, that nobody wants to raise this to the 4th power. I don't. Write it 4 times. FOIL it 3 times. Not feeling it. Especially when there's a formula right here. Bless you, bless you. So the formula says, all right. We'll save you some time. We say thank you, praise the Lord. So, if I want to raise it to the 4th power, the r, who is the 3, right? R cosine theta plus I sine theta. The 3 gets raised to the 4th power. So following the formula, if I'm trying to raise a complex number to the 4th power, r gets raised to that power. Cosine, after a lot of work, would end up being a multiple angle with that 4 theta. Ooh, but hold on, who is theta, guys? 60. Exactly. So do 4 times 60 degrees. And then the sine would end up with 4 times his theta. Oh, it's the same theta, 60 degrees. And so to simplify, can anybody do mental math with 3 to the 4th? 81. Yeah. 3 squared? 9. 3 squared? 9. 9 squared? 81. You have all 4. 81. What's 4 times 60? Uh-oh. I'm about to box it, but why am I going to have to go over to my computer and hit undo? Standard form. Yeah, the directions say, no, we don't want you to stay in trig form, we want you to go to standard form. The good news is you guys are allowed, remember this chapter, this test, you are allowed to use a calculator. That's not to have you study any less, that's to help you realize what you are allowed to do. So if I want standard form, we're going to go ahead and multiply that 81 in and say, oh, we got to get it to a plus bi form. No cosines, no sines. We got to plug it into our calculator. So you guys go to plug it into your calculator. I'm going to go ahead and move this I in front so you guys don't get confused with him. I'm going to go ahead and think unit circle, because 240 is 30 away from 270, which would be a 60 degree in the third quadrant. Cosine would end up being negative 1/2. Sine's going to end up being a negative as well. That's going to end up being a root 3 over 2. Now this is the nice perfect form. What do you guys get for your decimals? Is it negative 40.5? Nice. And then minus? 70.148. Now what if, let's just talk what if. What if you plugged into your calculator, got this on the test, but all the answer choices had these little numbers? You could try to make it match, right? Couldn't you go plugging this in the calculator and then seeing which one matches what you got? Okay. Let's say you plugged it all into your calculator, got these. Go back, check all the multiple choice answers and find the one that matches. Will it take more time? Yes. But the book's going to like the perfect answer if it's a unit circle one, whereas you're going to probably like the decimal answer. Just got to make it match. Is that okay? Just strategies. Here's where it gets funny. This whole root thing. Guys, the only thing that would have changed is if it was a 6th power, it would have been to the 6th, then 6 times. If it was to the 10th power, 3 to the 10th. 10 times. We can raise to any power and use this de Moivre's theorem. It only gets weird when we have these things called roots. Because roots can be written as fractional powers. We've seen this a lot this year. If I have, let me make it more general. If I have x to the a to the bth root, remember we can rewrite that as x to the, do you remember how the fraction goes? Who's on top? A over b? A over b. It would have been a 1, but I erased it and I put that little a in there. A, who's under the root, is the whole power. He's the numerator. B is how that power is being divided. Okay. A over b. The root is dividing the power, so that's why it's a over b. And de Moivre's theorem, basically, if I was to say, all right, let's go ahead and raise a z to the a over b. Let's say I see a root and I rewrite it as a fractional power. Then it's like, all right, I'm going to make r to the a over b. And then I have cosine of a over b times theta plus I sine of a over b times theta. That's technically, if we just outright apply it to the theorem, it's like, well, if that's the power, okay, fine, that's the power, and this power gets multiplied. That's a strict application of de Moivre's, but if you look down here, it looks just a little different. It looks just a little different. Now I'm going to go ahead and put this nth root over the z. I'm not sure why they don't. I think they're kind of assuming that the words are doing the math. So that gets kind of confusing. If you were trying to find the nth root of any sort of complex number, you would need to raise the complex number to the 1 over nth power. And it's like what we do to the z, we do to the r, and so that's why the nth root just stays there. But then I need to bring this 1 over n into the theta. Now the struggle is, we kind of saw this with cosine 2x equals when we were solving those nasty trig equations. If we go dividing angles by n, all of a sudden what was normally 0 to 2 pi just gets condensed, and so actually more answers are allowed in. Because as you're dividing theta by n, all of a sudden you're dividing the coterminals by n also, and it does not take 2 pi to get another answer, which means a few more answers might sneak in. So let me try to show you that example or an illustration as to how to remember this. I'm not sure the formula will quite do the trick. Last 2 examples. And get rid of all these lines. Cube root. Alright, cube root. Hopefully you guys know how to write that just normal-wise. But how would we write that as a power? Z to the power of 1 over 3. Okay, cube root, same thing as z to the power of 1 over 3. And that's going to help remind you hopefully a little bit. But you can also be looking at the formula. Remember, you're going to have these. It's okay. We're going to take the cubed, which is like the nth root, of r, which is the number in front. Don't I need a cosine and a sine? Look at your formula. Isn't the whole formula based on having trig form, guys? So I really want to take cosine of something over 3 plus 2 pi k, and I sine of something over k, something over 3 plus 2 pi k. But the struggle is, where's my theta? Let me find it. Yeah, what form did they give me? Trig form or standard form? Struggle, I need my trig. So to find trig form, we're going to actually have to review a couple things. And I'm not going to spend a lot of time on it because we practiced on trig form on Friday. You can go back and watch that part of the video, trig form. But long story short, we have to use our formulas in order to do 2 things. One is, well, actually, hold on. This guy's been factored out. If we multiply him in, we could actually rewrite this guy to be negative 125 all over 2 plus, actually it's going to be a negative 125 root 3 over 2i. That would be our standard form, a plus bi. Right now they have it all pulled out and factored. In order to find our r, we would have to go ahead and do the square root of a squared plus b squared. Let me help you out real quick. The crazy thing is after that, or after you plug in the a squared plus b squared, I can already tell you that your r is going to end up being 125. Which is a little weird, I know. But the reason I know this is because I can see a 1/2 and a root 3 over 2, and so I actually know already what my theta is going to be, because my theta is going to be tangent inverse of b over a, and if you were to plug this in, you would actually end up with, for our theta. Bless you, bless you. Let's see, we have a negative, negative, that's the third quadrant. This would be in the first quadrant, root 3 over 2 is your sine, 1/2 is your cosine, pi over 3. Do you guys remember in our notes that we wrote about when you find your theta, you have to use tangent inverse? But we also have to use tangent inverse and it's been a while, whole week. If you use tangent inverse, we talked about it with vectors, and we talked about it again in this one. It's okay, go back and look. Use tangent inverse and picture. If I was to graph this guy, he would be in the third quadrant. Because he's a negative and a negative. Both his A and his B are both negative, left and down. So pi over 3 is in what quadrant? How do I get from the first quadrant to the third quadrant? What angle measure do I need to add to get from the first to the third? 180 or pi. I'm writing it in radians, because that's how my formula was. So I have to go ahead and add pi, which will equal 4 pi over 3. Whew, took a little bit of work. If you guys had done it in degrees, no big deal, you just would have had to add 180 instead. That would have also worked. Okay, now we have it. Just for sake of simplicity, since you guys will think a little bit better in degrees, let me go ahead and change to degrees real quick. You're going to think in degrees better than you will in radians. 4 pi over 3 is the same thing as 180 plus 60, so that's going to be the same thing as 240 degrees. So I'm going to write 240 plus 360k, 240 plus 360k. Here's a W. Because of the cubed root, let me tell you a hint. The cubed roots, there are going to be 3 answers. Guess it's going to be true down here for the 4th root. Then there's going to be 4 answers or 3 answers. I just have to go ahead and plug in. When k equals 1, I apologize. If you guys look at your formula, it starts at 0, right? For this one, I would do k equals 0, 1, 2, and 3. I just have to go as far as many answers as I need. And then we're going to go and plug in. And a long story short, the cubed root of, I found my r to be different than I thought at the very, very beginning. I would end up with -5 cosine of 240 over 3 is 80, and 80 plus 120, there's going to be 80 degrees. I'm going to put the shortcut notation so that you guys can see me finish. -5 with 80, -5 with, I'm going to plug in when k is 1, I'm going to divide everything. 80 plus 120 will be 200, and -5, 80 plus 240 will be 320. Alright, kiddos. These are the hardest ones. The nice thing is we finished with 5 seconds to spare. I don't know why everyone always gets out early in chapel day. Sorry they distracted you. These are the weirdest ones at the very, very, very end. So, homework. Due tomorrow, we're in grade 6.5. And then tomorrow you'll be able to work on corrections and or test review for homework because nothing will be due on Wednesday besides just ready for our test. Michael, thank you so much for your patience. I know it was boring stuff today. After those formulas, tests are coming to me right now.
Also, my game is at 10 p.m. Oh, it's at 10 p.m. B squared plus C squared minus 2BC cosine. That's sine. No, that's cosine. That was cosine.
I'm going to put my stuff away. I'll be there soon.
No, I'm studying this weekend.
And the nice thing is, like, in that homework, you had to use it, like, it was a lot of work, and remember on the test,